We finally made it to the end of Unit 1 in Lesson 18 here, entitled Putting It All Together, because in this lesson we kind of looked at big picture of what we did this unit. We talked about dividing, factoring, zeros, graphs of polynomials. We kind of threw everything that we learned in this unit together, which is why it's one big monster of a unit. I promise the rest of them will be shorter and smaller. But we have one homework problem with multiple parts, so let's get to it. Let p of x equal 2x to the fourth plus 11x cubed minus 3x squared minus 4x minus 20. Explain why x plus 5 is a factor of p. So there's a couple ways we can do this. We can divide. That would explain why and hope that we get a remainder of 0. Or we could simply use the remainder theorem and plug in x equals negative 5. So p of negative 5, when I plug in a negative 5, what do we get? P of negative 5 equals 2 times negative 5 to the fourth plus 11 times negative 5 cubed minus 3 times negative 5 squared minus 44 times negative 5 minus 20. If it's a factor, this number, when I type all of that into my calculator, I should get out 0. So right now I'm grabbing my calculator and typing in 2 parentheses negative 5, close the parentheses to the fourth, plus 11 times negative 5 cubed, minus 3 times negative 5, close the parentheses, squared, minus 44 times, minus 44 times negative 5, minus 20. And when you type that all in, I got 0 out from my calculator. So explain why x plus 5 is a factor of p. Well, x plus 5 is a factor of p because x equals negative 5 is a 0. That's what the remainder theorem is telling us. If negative 5 is a 0, that's my remainder when I divide by x plus 5, then x plus 5 is a factor. So knowing that x plus 5 is a factor, factor it completely. So because I know it's a factor, that's telling me to divide. Because I know it's a factor, it's telling me to divide. And I can either do reverse tabular here or long division. I'm going to do reverse tabular just because I know it's a factor and it saves a lot of space. So I know it's a factor, so reverse tabular is pretty straightforward. I've got a 2x to the fourth and 11x cubed. We need lots of columns here. Minus 3x squared, another column. Minus 44x, another column. Negative 20. Okay, so I've got all of these columns here, and I'm going to stick a 2x to the fourth in there. So because I know x plus 5 is a factor, that means I can use division to get the other factor and help me factor this expression. So what times x is 2x to the fourth? 2x cubed times x is 2x to the fourth. We multiply down just like we would if we were doing long division. And if you're doing long division, the steps and the numbers are all going to be in the same space. It's just a different representation of it. I've got 10x cubed. I want 11 of them, so I need an extra 1x cubed here. What times x is 1x cubed? Well, plus x squared. X squared times 5 is 5x squared. But I want negative 3 of them. I've got 5, think of a number line. I need to get all the way down to negative 3, so I need negative 8 of them to make that happen, because negative 8 plus 5 gives me negative 3. Negative 8x times x gives me negative 8x squared. Multiply down, that's negative 40x. But I want negative 44 of them. I've got negative 40, think of a number line. I need to get 4 more negatives, so minus 4x. So I'm missing a negative 4 there. And it checks out. I'm left with negative 20. So this tells me that p of x can be written as x plus 5, because I know that's a factor, and the other factor is 2x cubed plus x squared minus 8x minus 4. Well, can I keep factoring this? Well, there's 4 terms there, so I'm going to try grouping. What can I take out from the first two? I can take out an x squared from those 2 terms. I'm left with 2x, what times x squared is x squared, plus 1. I need a 2x plus 1 over here. What do I need to factor out? I need to factor out a negative 4. Yes. So my factors of p of x are x plus 5. He comes along for the ride. My new GCF is 2x plus 1. And I've got that x squared minus 4. So I've got x plus 5, 2x plus 1, and then again, this is the difference of perfect squares, x plus 2, x minus 2. So that's p of x in factored form. It's an x to the 4th polynomial, which means I could have 4 linear factors, which I do. We factored p of x completely as the product of 4 linear factors there. State the solutions to p of x equals 0. What are my zeros? Well, let me look back here. I've got a factor of x plus 5, which means x equals negative 5 to 0. 2x plus 1, so if I have 2x plus 1 equal to 0, this is using the zero product property, I get 2x equals negative 1, so x equals negative 1/2 is another 0. What else do I have? Plus x equals negative 2 and x equals positive 2 from that difference of perfect squares there. So I get x equals negative 2 and x equals positive 2. Those are my 4 zeros. Describe the end behavior and sketch a graph. Well, the end behavior is saying as x approaches infinity, where's my function going? Where does p of x go? And as x approaches negative infinity, where does my function go? Well, remember, end behavior is determined by that first term when it's written in standard form. I have a positive leading coefficient of an even degree. So I have a positive leading coefficient and an even degree. So think of your dance moves. Even, odd, odd. I've got an even degree, so it's one of the first two. Positive leading coefficient means the end behavior looks something like that. I know you're doing the dance moves in your head right now. So as x approaches infinity, my function goes up towards infinity because my right hand is pointing up towards the sky. And as I approach negative infinity, my left hand is pointing up towards the sky. So that's what my end behavior looks like there. So when I go to sketch a graph of this, using those ideas, well, my zeros are at negative 5, negative 1/2, negative 2, and at 2. Those are my zeros, and my end behavior, my function, is behaving like that at the end. So it's going to come through, cross through, and then shoot off to infinity. That's a sketch of p of x here, based on the zeros and the end behavior. So this exercise here put everything that we learned together from this unit kind of into one problem. We talked about the remainder theorem, we talked about how we can divide and how we can factor expressions completely. In this case, we had to factor by grouping and then use the difference of perfect squares. We talked about the importance of solving polynomial equations equal to 0 by using the zero product property, which is why it's important to have it factored. We talked about how we graph polynomials using end behavior, the zeros, and multiplicities. We didn't have to talk about multiplicities in this case, but that is a key feature that we talked about. So congratulations, we made it to the end of Unit 1. See you in Unit 2.